Hi everyone, welcome to the channel. In our series of lectures on substitution techniques, today we will learn about one-time pad. In case you have not gone through the previous videos on other substitution techniques, please check them out in the description box given below this video. Now we'll learn about one-time pad. So one-time pad is basically an unbreakable crypto system which actually provides 100% complete security. It is said to be an improvement to the Vernam cipher, and it is jointly developed by Vernam and Mebon around 1918. And here, how it proceeds is in one-time pad encryption, the message is represented as a sequence of zeros and ones. So either you write out all the numbers in binary, or you start by using the ASCII. So the key which is used in this one-time pad is a random key, and this is what makes it 100% completely secure. This is a completely random key which is randomly generated, and its length is as long as the message. All the letters of the key are completely random, and they don't have any statistical relationship with the plain text or with the ciphertext. So there is no need to repeat the key here. And this one single key is used to encrypt and decrypt a single message, and after its use, it is discarded. So if for a second message, if you want to generate a key, you need to, if you want to use a key, you need to generate a new key of the same length as the original plain text. The key should be of the same length as the plain text. And so every time whenever you want to encrypt and decrypt, you're going to generate a new key, which is also completely random and of the same length as the plain text. That's why this one-time pad scheme is unbreakable and a completely secure crypto system. So when whatever output is produced by using the random key is completely random, and it has no statistical relationship with the plain text or with the ciphertext. So since the analyst will not be able to get any type of information by getting hold of the key or from the ciphertext, there is no way to break the code. So let's see how encryption proceeds in one-time pad. So as I told, the message is written out as a sequence of zeros and ones in form of binary. So since we are working with binary, we'll be doing mod 2 bit by bit. So if you are in possession of the plain text and the key, we start by doing XOR operation bit by bit of the bits in the plain text and the key. So we use the following rules, like 0 plus 0 is 0, 0 plus 1 is 1, and 1 plus 1 is 0. So for example, if you have the message 00101001 and your key is 10101100, then how we'll be obtaining the ciphertext is we'll be performing XOR of this plain text with the key bit by bit by following these rules. So here your plain text contains 00101001. That is, we perform XOR operation of each bit of the plain text with each bit of the key. 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, and so on. So finally, we obtain the ciphertext 100000101. So to perform the decryption, we will be doing the reverse operation. We will be performing the XOR operation of the ciphertext with the key. So simply perform the XOR of the key onto the ciphertext. So here our ciphertext was 10000101, and we'll perform XOR operation of it with the key, which is 10101100, to get back the plain text. So alternatively, we can also represent the plain text as a sequence of letters. So in that case, when we make use of one-time pad, the letters are represented by using their alphabetical equivalents like this. Suppose if our plain text is COMETODAY, come today, then each of these letters are represented by using their numerical equivalents, just like how we saw in the previous videos. So A is represented by 0, B is represented by 1, C is represented by 2, and so on, and Z is represented by 25. So in that case, C is represented by 2, and O is mapped to 14, M is mapped to 12, E is mapped to 4, and so on. Then we have a completely random key, which is generated by using a random sequence of shifts between 0 and 25. It's a completely random key obtained by randomly shifting the digits of the, randomly shifting the letters of the alphabet. So a completely random key is generated, which is NCBT ZQARX. That is also converted to its numerical equivalent. And then we add up the numbers of the plain text as well as the key. We get 2 plus 13 is 15, 14 plus 2 is 16, 12 plus 1 is 13, 4 plus 19 is 23, 19 plus 25 is 44, and so on. Once we get it, since we are working with letters, we have to perform mod 26 operation. And when we perform mod 26 operation, if the total is greater than 26, then we would be subtracting 26 from the number. So 44 is greater than 26. So we subtract 26 from 44 and we get 18. If it is less than 26, it remains as such. If it is greater than 26, we subtract 26 from it since it is a mod 26 operation. So 47 minus 26 gives you 21. Finally, you convert the numerical values to their alphabetic equivalents and we get the ciphertext as PQNX SE Same way it goes on for decryption also. For decryption also, we use the same key and the ciphertext. And to get back the plain text, instead of adding the shifts, we will be subtracting the shifts. For example, our ciphertext number is 15 and our key is 13. So while doing decryption, we'll do 15 minus 13 is 2. 16 minus 2 is 14. So we'll be getting back the plain text as O. Similarly, 13 minus 1 is 12. So you will get back the plain text as 1. So 13 minus 1 is 12. So you'll get back the plain text as M. So in this way, it proceeds. Same way, here you have 18 minus 25. So when you get a negative, you will be getting a negative value as result. So when you get a negative value as result, you add 26 to it. And so 18 minus 25, you will get minus 7. So minus 7 would be plus 26 would be 19. So in that way, we will be getting back the plain text during our ciphertext process. So let's see how one-time pad offers complete security. So this shows two types of ciphertext, the same ciphertext with two types of keys. Two different completely random keys are used to encrypt these, to decrypt the ciphertext. So in this case, you can see that since the key is a completely random and different key in both the cases, so what happens is two different plain texts are produced. Let's say if the cryptanalyst gets hold of both the keys, if he tries to decrypt the ciphertext with the key, he gets two plausible plain texts. He gets two plain texts which both appears to be intelligible. There is no way for the attacker to identify which is the correct key or which is the correct plain text, because there is no statistical relationship between the key and the plain text or between the key and the ciphertext. So even if he gets hold of the key, the cryptanalyst will not be able to make any type of statistical analysis and get hold of the plain text or the key. And so that's how that's how one-time pad is completely unbreakable and provides complete security. So disadvantage of this one-time pad scheme is, for every message encryption, you need to generate a random key which is of the same length as the message. So practically you need to generate large number of random keys. So at least practically, a truly random key can be generated only by using quantum computers. So currently we make use of pseudo-random number generators for generating random numbers. So if it is a heavily used system, it may require millions of random characters on a regular basis, and that practically it poses a lot of problem. The second problem is, once you generate the key, you need to protect the key as well as you need to distribute the key securely on a secure communication channel. So, and because you need to generate a key which is having the same length as that of the plain text or the message, that has to be sent to both the sender and the receiver. So key distribution as well as protecting the key is also another disadvantage of this one-time pad scheme. And for this reason, this is primarily used only for low bandwidth channels which require high security. So that is all about the one-time pad scheme. With this, we complete all of the substitution techniques under our topic of classical encryption techniques. Thank you.